Hello, so this is the additional material explaining the operation of the provided Viterbi detection function that you can use to finish the practical exercise 7. Now, if you have access to MATLAB, you are welcome to use the built-in function, which is better. Yes, it is better in a performance sense, in a convenience sense, and so on. But unfortunately, as we all know, MATLAB is a commercial product, so it may not necessarily be available to you outside of a computer class. So here I would like also to mention that next week we are going to have a consultation, and if you need to access a computer class in order to use some specific MATLAB features, we can arrange that, no problem. So, considering that you will use Octave or any other free alternative to MATLAB in MATLAB language, you are going to need your own Viterbi function, which I have provided for you and which you can see now on the screen. In the practical exercise video part 1, we already used that to perform the detection. I have seen that it achieves almost optimal results, as if no interference was in channel. However, it does so with some specific time, and for our needs of training and study, this is acceptable. However, in real world applications, of course, we need a better implementation than provided here. Still, it is very recommended for you to study this code to understand better, and maybe then you can have your own ideas how to improve this operation. So we start with a very simple program that we have made for our practical exercise number 6, when we had this task of making a decoding procedure by hand on the paper or sheet or in the computer program, whichever is more convenient for you. So the task was to actually go through the entire process of Viterbi decoding, yes, that is equalizing nonlinear, and accordingly we had some specific symbol sequence that was very short, and your task was to study it. And in the process of doing so, we also made a small assistance script that was used to calculate these metrics of the states. Yes, so for the choosing the most appropriate transitions from one state to another, and this way making the modulation. So examples of these metrics are here and here. So for each symbol we have obtained all these metrics. Furthermore, the program chose the smallest values of these metrics for us, as you can see here in the first step. Yes, there are actually two competing metrics for this input state. Yes, so let's actually let us also bring the state diagram of our channel. So as you can see, for the state 1 here there are two competing paths, this one and this one. So the first path has metric 0.34 and the second path had metric 2.52. So out of these two we had to choose only one with the smallest metric, so we did so, and the program we designed did actually that for us. So for more details, please see the practical exercise, previous practical exercise, exercise 6, I believe that is in this semester. So if you happen to watch outside of my course, which I can see sometimes happen, then there is a previous video for this program. Yes. So okay, now having that program is not really very good for us, not really suitable for us. Yes, in multiple senses. Well, first of all, we will want to use the input symbols +3, +1, -1, -3, or maybe even higher order pulse amplitude modulations, which are orthogonal projections of the quadrature amplitude modulation, right? So we have plus 3 plus 1 minus 1 and minus 3 on one axis, and the same options on the second axis. So in total together they make a quadrature amplitude modulation 16. However, each axis separately is just a pulse amplitude modulation 4, which is the square root of the total number of these points, which is less number of states. However, this PAM4, as I mentioned, uses 4 different values of symbols, and our program was made to consider just the binary case. Yes, well, not really binary, this is actually PAM2 or NRZ or whatever else we may call it, but still only 2 values. Yes, so we will need to change that. So what will change with that if we have a greater number of the possible symbol values? So we are considering the same impulse response consisting of these 3 values, right? The initial current moment value and previous, also previous before that. So 2 previous values of the symbols are affecting each current received symbol. So it's still the same. This means that the total number of states in our particular case was 2 as a base for our symbols, either +1 or -1, at the power of length -1, which was 2 at the power of 2 or 4. Yes, so 4 states, as you can see, they are all mentioned here. No other state would be possible. Now from each of these possible states there are alternative paths which are sending either +1 red or the -1 blue. Yes, so this way it works. What will happen if we have more than this is available in this short demonstration presentation. Yes, let me actually zoom it a little bit. So here you can see that now our state can consist of symbol +1, +3, -1 and -3 in different combinations. So in total it is possible by using 2 previous symbols to arrange 16 different combinations, which would be 4 as the power of L-1. Now we have a base 4 for symbols, so we have 4 different symbols, so we use that. So that gives us 16 possible states, and now from each state we can have 4 different transitions. As you can see here, we can send +3 in red, +1 in orange, -1 in teal, and -3 in blue. Yes, so all of these paths originate from each of these 16 states and end up within another of 16 states. However, as you can see from this picture clearly, yes, there is a certain law to how these states end up in the same state. Yes, so all +3 states for the first 4 states end up in the +3 state, and that is the, how we can say, achieved thanks to the specific order of assigning this, of arranging or sorting these states. Yes, so we want to arrange them specifically this way so that it will be much more convenient to organize this in our algorithm. Yes, so here we can see that we basically have it already. So +1 +1. Yes, so this is a previous state, this is a state, not state but symbol, previous symbol, this is the symbol 2 symbols ago, and this is the currently transmitted symbol. So the state is the same and the currently transmitted symbol is different. Yes, so now we are going to need to have, well, let me actually type it here nearby in the comment style. Yes, where is that? Here. Yes, so that would be +3 original state, and now from this state we can send +3, or we can send +1, or we can send -1, which is also from this state, or we can send accordingly -3. However, all of them are going to end up in a different states. So +3 is going to end up in first state, +1 in a state with number 5, -1 with state with number 9, I believe, and -3 in the state with number 13. Yes, by 4 each time greater. So this may not be really convenient once we organize this as a matrix of weights for us to calculate. So here you can see that we calculate all the possible state values for the channel. Yes, once we send any of these combinations through our specific channel, we have a knowledge on what is going to be the transmitted symbol. For example, these, and they are arranged here in groups, yes, for the incoming symbol for this. Yes, so as you can see here, for this symbol, first two values represent these two paths, 1.4, 2.4. For this second one, this is accordingly 0 and 1. For the third one, it is -1 and 0, and for the fourth one, accordingly, this is -2.4, -1.4. Now, because of that, we have to actually, considering that our weight matrix, let me remind you, this weight matrix, yes, it's actually available also here, is organized in a sense that each number of the raw number represents this state we are ending in. So this state is for the first row, this state is for the second row, and so on and so on. Yes, accordingly next, but wait a minute, I believe this is not correct currently. I have already changed this program, so I'm a little bit confused as to why it is now showing different results. But wait a minute, I haven't run this program, it's some old data. Yes, so now it's here. Yes, as you can see here. Well, we don't really care now for AVGN. Here is this list of all the possible states. This is one state, this is another state, and another state. And for each state there are two possible transitions. So this first transition yields this output symbol, this transition yields this output symbol. So now, as you can see, we are basically opposite organized. So we are now considering the originating state, not the where we end in, so where we start from. So for this first point we have specified 1.4 and -1. Yes, now these all are for the state 1 where we go from. Now the next accordingly are 2.4 and 0, 0 and -2.4, and 1 and -1.4. Yes, so it's opposite to what I said. Yes, or what I said was what we desire, but what we have now is the actually opposite. So okay, now we have to do something about this AVGN. We are going to simply comment this. I don't want to load any toolbox now. So here is that weight matrix. It's exactly the same as in that example what I have shown. However, now you can see that we need to so each row, as I said, is a state we are going to end into. Yes, so basically this, and this, and each column is accordingly is the state we are originating from. So these, and these. So accordingly we can see that we end up in state 1, first row, either from the first state or from the second state. Yes, and this is what has been transmitted in the process. So in the second state we end up originating from the third and fourth step, and then it repeats. So if we check this list of possible signal states in the channel, yes, we can see that we need to assign them by skipping one value. So this and these go here, then these and these go here, then we start over and send this one, oh sorry, -1 here, this 0 here, this one here, no, one already used, sorry, -2.4 here and -1.4 here. So we have to skip them by 1. So if we are going to increase the number of possible symbols, we are going to use a state, then skip 3, next state, skip 3, and so on. So it's possible to be calculated, but a little bit maybe inconvenient for us. Yes, so here you can see first, third, fifth, seventh, 8, 4, 6, 8. What it would be much more convenient for us is to organize it as follows. Yes. As follows, so that we assign to the first row 1, 2, to the second row 3, 4, to the third row 5, 6, and for the final row 7, 8. So they are consistent and following one another. In order to achieve that, we need to change this order here, yes, so that basically first column isn't changing and the last column is changing, yes. So we end up with this alternative version, yes, when this is the current symbol, and as you can see it is the same for all the first 4 values. This is the state 1, state 2, state 3, state 4, and from all of them we send +1. And this is accordingly -1, which is also sent from state 1, state 2, state 3, and state 4. So the only difference is basically the order of how we are choosing this state. So let me choose some, I don't know, green color and explain this visually on the state diagram what changed. So previously here in this situation, yes, what we did was we started with this transition, then next transition we calculated was this transition, then next this, next this, next this, next this, next this, and finally this. So that is how we did before. So the order of arranging these possible transitions in this state diagram matrix, yes. Now the new order is a little bit different in a sense that we want to consider following. First we analyze this transition from state 1 sending +1. Next we analyze this transition sending from next state also +1. Next we analyze this, next we analyze this, and so forth. Yes, so as you can see, first we go through all the +1s, and only then we go through -1 paths. Yes, so if we do it like this, then if I run this program now, yes, you will see that our symbols are already grouped as we desired. Yes, so these two go here, these two go here, these two go here, these two go here. Yes, so this is very convenient for us. At least convenient to the way I have decided to organize this algorithm. Maybe it's not the only possible way, but well, to explain it better, I believe it was necessary, yes? So what we do next is try and program these to be created, because you don't really want to now make all the matrix for the PAM4. Yes, I believe I didn't do it even. Yes, I decided I want to solve this problem programmatically. So that is a problem when you have +3, like, I don't know, +3, +3, +3, all that 16 different states you are going through. Then you go with +1 through all 16 states. Then you go with -1 through all 16 states and so on. So that would be 64 rows, yes, and 3 columns with all different values of these. It could be written manually, however it would occupy much space and also, well, not really help us if we decide we want to use even more possible symbols. For example, +7, +5, +3, +1, and so on for, let's say, quadrature modulation 64. Yes, so that wouldn't help us, yes, to write down even greater matrix manually. So we automated this process. So first of all, what we can see here is the specific structure of this matrix. Yes, so here you can see we have groups of the symbols, +1s, -1s, and each group here in the first column is 4 symbols long. In the next column it is 2 symbols long. In the next column it is 1 symbol long. And there is a total, yes, of 1 repetition for the first column, 2 repetitions for the second column, and accordingly 4 repetitions, yes, for the last column. So otherwise this is simply repeated versions for which you use a Kronecker multiplication. This Kronecker multiplication repeats each of our alphabet symbols defined by this u, yes, +1 and -1, 4 times, 2 times, 1 time, and so on. Then, once we have this entire vector, we replicate this vector accordingly here once, here twice, and here 4 times in total. Yes, so running these lines would provide us this matrix alone, just in 3 rows. But again, we might have longer impulse response, so we may need a 4th, 5th column and so on, which would require you to add extra lines for each impulse response sample, which is already much more convenient. But you will have to change these numbers to accordingly 8, then 4, 2, 1, and so on. And here in reverse order. First thing you can see probably is that these are actually in reverse. Yes, so no need to specify it as a hard-coded number. We can actually expect to reuse the same number. Furthermore, this is actually related to this value k. Yes, so if we organize this in some kind of a loop, expressing some parameter k of the loop, for k equal 1, number of repetitions can be accordingly expressed as 2 power of k minus 1, yes, so that would be 2 power of 0, 2 power of 1, 2 power of 2, and number of, well, basically length of the symbols per one column is accordingly reversed thing, number states, which is in total 4 in this example, divided by the number of repetitions. Yes, so 4 divided by 1 is 4. 1 divided, yes, 2 divided 4 divided by 2 is 2, and 4 divided by 4 is 1. Yes, so this way we find this. Accordingly, now we specify this as a parameter, and as you can see, finally we simply merge them together, yes, in one matrix. And so finally, as you can see, we can loop this process and repeat it as much times as we need by generating this state diagram matrix. So here you can see that this is generated like this, and no problems whatsoever to generate it for PAM4 also. Here is exactly the same script. Yes, so I'm going to now uncomment this just to show how it will look. So this is this big matrix, which I didn't want to write down by hand for this short impulse response. Now, we in practical exercise used even longer impulse response, which would require me to multiply this length by 16, I believe, yes, so that would produce 256 states, and it would be a 5 columns, which is completely too much, yes, to write down by hand if you decided to change your impulse response. So it was necessary to automate this process. Okay, next thing is the same. Yes, we calculate the possible states of our channel, and then finally we can arrange the matrix of weights. So let me remind you the idea of its operation, how it worked. Yes, so each symbol was calculated for each received symbol we calculated a Euclidean metric between these original possible state and uh, received symbol, which was a distorted version. So it ended up into calculating for each of these points. Yes. So here we can see all of them, all the possible states, which is 8 of them for 4 states. Yes, accordingly we calculate for each of this path its own state. Yes, and each, as I mentioned, this output state is one row here. So as we know from the algorithm operation, yes, we only choose the path with the smaller metric or the smaller weight. So we will need then to find the minimum of these weights in one row. For that instance, for that reason, yes, we initialized it with infinities, because infinity is always going to become even greater and greater. It's never going to be chosen. Yes, we will choose only either one of these when we search for minimum. So now this matrix is quite simple weight matrix, which we will use to actually calculate all these metrics. Is quite simple to organize. These two go here, these two go here, and so on, right? No, wait a minute. It's still incorrect code. Yes, so I'm going to maybe even close these. Yes, these two go here, these two go here, and so on and so on. So for the pulse amplitude modulation 4, yes, we are going to want, I'm going to output this matrix now. VG matrix, yes. Well, I can actually type it here. Have much bigger. First of all, we are going to have 16 possible states. Yes, and for each of these 16 possible states, as you have seen here, there are 4 paths. Yes, 4 incoming paths, and accordingly, as you can see from this diagram, yes, they are grouped, yes, depending on the transit symbol. So here you can clearly see 4 values here, 4 values here, 4 values here, and finally 4 values here. Then the process repeats. Yes, so now we assign them by 4, which is the number of the possible paths for each state. Yes, so accordingly it doesn't help us to use any specific hard-coded numbers, and we again have to somehow try and organize these as a iterative procedure. Yes, so here I have started doing so, yes, by assigning to the first row, first and second element these, to the second row, third and fourth element next 2 values, and so on and so on. So each line makes 2 values of this matrix. However, this is hard-coded, and in case something changes, we have to rewrite this part completely, which is inconvenient. Yes, for that reason I have organized the same procedure in a for loop. Once again, we go through all the possible states. This is the number of states, which is 4 for this example. And what we do here is we find out this range 1, 2 for the first state, 3, 4 for the second state, 5, 6 for the third state, and so on. We express it as a k minus 1 multiplied by the number of symbols, which is 2. Yes, so for k equal 1, this whole thing is going to be 0, and this accordingly is 1 to 2. If k is 2, this whole thing is going to be 2. This is also 1 to 2, and according 2 plus 1 to 2 is going to be 3 to 4. Yes, and so on. So that is the main part. Now please note that here, once we reach the final state number 4, we have to start over again repeatedly, yes? So for this reason, here we use a remainder calculation, yes? So modulus algebra. We can say that this is basically mod 4 plus 1 for our index outval, yes? So we apply modulus 4 algebra to these indexes and force them to become in range from 1 to 4, yes? And as you know, modulus algebra can never produce 4 after dividing by 4, so we extra add plus 1 to convert 0 to 1 and 3 to 4, because MATLAB starts indexing from 1, as you know. Then we use these periodically repeating indexes here and normal regular indexes here, yes, in this assignment, much like this is actually this row, yes, or this row. The only thing that changes is these indexes. We go through rows regularly key, this is the numbers of columns, and so on. So accordingly, after we do this, our matrix of possible weights, yes, of state diagram of a channel accordingly is prepared, and we can now have it for any length of the impulse response. So for example, I'm going to now add one more value of the impulse response, and no, sorry, I can't do that because this is hard-coded. I can do it here in this program, which is completely universal, I believe it should be. So if I add one more impulse response value here, yes, as you can see, now it's even bigger. So what we want to know is the dimension 64 by 64 now, yes? If I add one more, it's going to become 256 by 256. It would be too crazy to write this manually if we decide. And we, let me remind you, in practical exercise, did try this value out, yes? So this concludes that part which was necessary to automate all of these preparations for the algorithm. The algorithm itself here, however, is pretty universal as it is, yes? So if we check this here, well, you can see it's exactly the same. Don't pay attention to this. This is only needed to produce some output during the simulation, so that you know that your computer hasn't frozen or whatever else, and that it is doing something, yes? As for this part, it's exactly the same as it was in our practical exercise previously, yes? So this calculates it. Yes, this is the history of accumulated weights, which was not previously, yes? So here you can mention that the only repeating part is here, which actually symbol by symbol applies metric calculation, chooses the minimum weight, updates the metric, and continues on to repeat this process. So here what we want to do is to store these minimum metrics in the array so that we can use that later to find the path. Because in practical exercise 5 we use this program only to calculate these numbers, and then we took our pens or pencils or whatever else and manually found backtracking the path to read the symbols, yes? Now we need a program to do this for us. So for this reason we need a history of weights and also a history of the states originating from. So for this, for example, state, we need to remember that currently minimum weight, minimum metric is 19.56, and that this path comes from the state 1. Yes, so this is what we need to store. Yes, let me remove that extra impulse response value I added to make things a little bit shorter and show you this example. So for this output, yes, here you can see the history of the weights. So for each state we have calculated one of the 4 possible weights and chosen the smallest one and stored it in this array, yes? So accordingly, as we know, the path would be to follow the minimum weight. Yes, so that would go here and here. So which is not so difficult to do in MATLAB, to track these minimums per each column and accordingly find indexes and so on. Which would be more difficult for us is to know where in our state diagram here this path actually comes from. For this reason we need to have this array. Yes, so if we know that this is the minimum weight, yes, then we accordingly find out that this is a column number 16, 15, 14, 13. Then we look up the column 13 in our history of indexes, and we found out that we need to go to the state 2. Now state 2 needs to go to the state 8. State 8 needs to go to state 13. State 13 needs to go to state 1. State 1 needs to go to state 4. State 4 needs to go to state 16, and so on. Yes, so this way we are actually able to backtrack by using the minimum weights and the information about what was the previous state number. And this is used to actually perform the backtracking. It's not available in these simple scripts, it's available in the final version of this code. Yes, so let's analyze this. So this is history calculating. I added a lot of commenting here for your convenience and studies, yes, but here what we actually are doing now is to try and calculate the path with the smallest matrix. So before we continue, let's maybe have some example here when we had an error. Yes, so an error because of the noise, which is completely possible, too strong noise happened here, yes, led to the condition that our path with previously smallest metric here, as you can see, at some point discontinued. Yes, as you can see, it didn't get any continuation here, so it was extinct. Yes, and other path with greater metric here continued. Now at this step I need to mention that I after I believe step 3 started to normalize metrics. Normalize means that I deducted from all these columns the smallest value. Yes, so that smallest value is always 0, so that these metrics would be easier to follow the true path. Yes, so here you can see that this error, this too strong noise, actually led to the situation that we diverted from the true path and went some wrong path. This resulted in 2 errors. Yes, whereas real problem with noise was in only one symbol, which is possible. That is the problem that can happen. However, here you can see what was the true path and where that error actually has happened. Yes, that error has happened here at the symbol number 10, when somehow noise was so strong that this metric, yes, for this input path, no, wait a minute, here it happened, yes, because it could have gone like this also. Well, honestly, it's difficult to now tell where exactly it went wrong, but the problem was definitely here. This is the only symbol that changes, right, from this trajectory, so it merges. Either way, what's most important thing is that after this step, it still merged with the correct path. Yes, so and here it started to divert from the correct path, here it merged back. So either way, even if errors do happen, which are unrecoverable, yes, sooner or later the path is still going to merge and return to its base, to the correct form, yes. Now what we want to do is to read this path from this trellis, so as I have shown. However, it's not as simple as I have shown here, that we simply follow the smallest path. That is not actually true, yes, and that was one of the reasons why it took so long for me to understand how to write this algorithm. What we need to actually consider is the accumulated total path weight for each of the survived paths. So here you can see the idea that in order to start reading and be certain about the results, we need to skip some part where it still branches, yes, and if we still insist on finding some possibly best solution, we need to analyze each of these paths. So that would be this path and calculate all the total metric, adding up metrics from each of the point along this path to this one total number. Yes, same needs to be repeated for this path, for all of the possible paths. Yes, so what we are going to do here, you can see 4 different possible paths. That would be 1, and then it continues that it could be path here, it could be also path like this or path like this. So in total 4 different paths, and further after this point they go the same. Yes, so we calculate the total metric by adding all the numbers along this path. Yes, so up to this point the total metric was 32.55, so we add 0, we add well, no, up to this point, yes, we add 0, we add 1.49, for this path we add 0 and 0, yes, that is third. For the second state path, that is 540 something, yes, and 462, and so on. Then we choose the smallest one and consider that this was actually the true path, which is in bold here. However, if somehow we would not be in rush and store all the possible transitions. So previously, as I mentioned, we discarded the path with greater metrics. So for this specific point of the problem, yes, there were 2 metrics, 2.17 and 6.1 for this path. Obviously 2.17 is a smaller value, so it is kept, and this is discarded. Now, if however we were to keep this path along with all the other possible transitions, so for each point then we would have 2 inputs, not 1, which would require a lot of more memory, yes, still. If we were able to do this, then analyzing countless number of this path, there wouldn't be 4 paths, there would be like 4 at the power of 18 paths, total possible paths, yes, which is, well, we can actually calculate how much is that, but that is a big number. And only one of them will be the minimum, yes, so it is calculated in billions, yes, 68 billion possible paths for this short 18 symbols long sequence, yes, and you need to imagine that in telecommunications we send them megabits per second. 1 second is 1 million bits, yes, which is completely unviable to implement. But still, completely out of curiosity, if it would be possible and we would calculate the total weight for each of these paths, then that would produce the smallest value, so the smallest metric for this particular path, and it would read correctly without error. But as I mentioned, it is simply not practically implementable to store all of these paths for such long durations. We can maybe store them for like 10 or whatever else symbols, yes, but not for the complete signal that we are receiving. So we have to choose, yes, and discard one of the paths to reduce the complexity of reading to the number of possible paths equal to the number of states, basically, yes. So with that in mind, we need to realize that we have to calculate the cumulative weight, yes, sum weight, which initially we assign, wait a minute, where it is, equal to the last column of these weights, yes. So we assign these as initial values of these weights. What we do then is we take each of these values, these for example, then we find the matching the source. So basically that means that we go to this weight from this weight, add it together, so now we have 54.68 for this path. Next, for this we need to go from state 4, so we add 6.5 and end up with 60 0.51 and so on for the entire path of our signal. Yes, we do this for each of these 16 paths. We end up with having 16 maximum weights. Yes, so sadly I can't run because this is a function, but the idea here is this, that we use this index history to find the source of the previous state, and that source of the previous state is used as an index to find its weight. Yes, so basically the meaning of this line is that by using this as address we find out what is this value. Yes, so we find the on the previous step first state's weight and add it to the accumulated one. Yes. Next step, we find from the state 4 in the previous this weight and add it together. So we repeat this process for each of the possible paths. Yes. In the matrix form here, so we don't need the second for loop. We do this in the entire matrix, and once we have done it, we need to find out what is the minimum total weight. Yes, out of these 16. So let's consider, for example, that it's going to be for this point. Yes, and then we are going to simply backtrack these through this states array. Yes, so accordingly we search this minimum index in this index hist, yes, in order to find out where we originated from. So for example, in this case that was here 2, that meant we went from this state 2, and now what we need to do is to understand, is it plus 3, is it plus 1, is it minus 1, or is it plus or minus 3. Luckily for us, there is a pattern which we have noticed at the very beginning. Yes, so as we can see, no matter how we can say which of these 4 paths went from here, from this point, that this point is plus 3 or minus 3 plus 3 alone defines that the transmitted symbol was minus 1. So basically we can conclude what symbol has been transmitted based just on the number of these states. So accordingly, these 4 are plus 3, these 4 are plus 1, these 4 are minus 1, and these 4 are minus 3, because the first symbol, oh sorry, I didn't capture it. Because first symbol of this new state is actually what has been transmitted in the process, yes, and they are organized like this intentionally, with this in mind that we will want to read it. So all that we need to do is to prepare the so do we have U? Yes, we do have U, to prepare again replication of these vector. So now we need to repeat 3 4 times, 1 4 times, minus 1 4 times, and minus 3 4 times. Yes, so that it would be done like this with a Kronecker multiplication, like this. Yes, and now accordingly it's only be a matter of matching this number of row with this symbol. Yes, this way we get the final result. We repeat this for each column by tracking the path. Yes, so this goes to 2, so now we are going to use 8. 8 is accordingly plus 1, yes, and so on. So we repeat this process by following this map and end up with a received data sequence here. Yes, so we read this from our map. Accordingly, finally, there is a matter of adding the delay, because as we have mentioned here, yes, there is some interval where we are not really certain if our red path is correct, so we need to exclude that branching part from our results to be sure that what we have is here the only and possible path that we can safely detect and read the data from. Yes, we don't try to read data from here because we may make some unnecessary mistakes in the process. And once we receive more symbols, these branches will stop branching and will merge with the one and only path. Yes, so it is only a matter of time when these will stop branching as you receive more and more of new symbols. So we need to introduce this additional delay as it is mentioned here. Yes, this delay is usually around 5 times by length of the impulse response minus 1. Yes, so if my impulse response length was 3 values, yes, so 3 samples, then I should use at least not less than this number to wait before I start reading my data. This is specified as a parameter of this function. Finally, this function stores all of these received data, history, and index history. So let's just for interest try and use these for the wait a minute. Well, actually I need to go one level up, make some new script here to implement this function. Let's say test script of some kind. Yes, CLC clear. Now what I want to is to use the same data sequence and impulse response as in practical exercise 6. So actually you may also use this function now for the practical exercise 6 because it can calculate all the paths, all the branches and so on. Now I have this sequence. I'm not going to add any noise. I need to generate the channel distorted version. So I send through channel, and accordingly now I'm going to try recover these y's, yes, and get symbols A. So for this I'm going to use, since I have plus ones and minus ones only, I need to change the alphabet in this function inside. Yes, don't, it's expecting to be a column, so you need to keep this formatting. Now it's going to work with the plus 1 minus 1 only. This could have been specified as parameter here honestly, but for the practical exercise we don't really need to use these. I'm just showing you what you need to change if you decide to use this function for your practical exercise. Then we copy this part, yes. Here we specify our y, here we specify our channel impulse response. It's still necessary to know 1, and here some delay, let's say 10. Of course, for this number of symbols probably we are not going to receive all of these symbols, but just let's watch what is going to be obtained. Yes, so received data is plus 1 minus 1, plus 1 minus 1, and well, other is unavailable yet because of this delay 10 symbols, which is exactly these 10 symbols which we couldn't see yet. Yes, if we had more symbols, let's say I'm going to add few more, then this would accordingly produce 2 more symbols of this row. Yes, as your new data will arrive and so on, you will have more and more of these symbols. Now here you can see the weight history that you need to draw this picture. Yes, well, actually these are these numbers, and you can also see where this path comes to this state from. Yes, so you are more than welcome to use this function. Now if you have MATLAB, however, yes, I believe I did have somewhere in the back MATLAB. No, not in the back. In checks maybe. Yes, but it's continuous one. We don't really want to use continuous one. Here it is. Now in Octave clearly this will not work, but actually in MATLAB there is a similar function which works faster and better called MLSE-EQ. It requires communications toolbox as well, so you need a license both for MATLAB, both for that toolbox, but in case your university provides or whatever else, yes, you have it, you may use this function. It works much faster and produces the same result. Yes, I was very keen on trying to get my function work exactly as the MATLAB one, and here you can see that bit error rate is exactly the same, and it is almost perfect for the CAM16 without any symbol interference. Yes, so this perfect channel with noise, yes, of course, bit error ratio has been calculated according to this formula just mentioned. Here is extra 3, which is skipped in this presentation because of my small mistake, yes, and you can anyway see more details about these formulas on this web page, yes. So here you can see that 3 is present there. So you are more than welcome to use this function to try to improve it, and if you have any more questions, feel free to address me. I will help to answer your question. I hope I will be able to answer your questions. So thank you for attention. This was additional material for better understanding of this function.